Thanks first for having me here and giving me the opportunity to talk, and also thanks to both of you for paving the field as it is by explaining why formamide, which is this peptide bond which we've synthesized, is so important. I mean, apart from the fact that it is the first and simplest peptide, it also has a host of other interesting reactions it can do to give rise, for instance, to the nucleobases. Also, it's been used as a solvent, and we've heard a lot of that. So, as it says in the title, I'm working with slow electrons, and the whole concept of using slow electrons might be a rather new or unsuspected one, because it's never really been looked at in astrochemistry a lot. So the electrons we are using have an energy typically between, say, 2 and 20 electron volts, which starts from about thermal energies. So 2 eV is actually red in color, to 20 eV, which is pretty extreme UV radiation, but that's the kind of energy gap we're looking at. So most of the interesting stuff happens where also UV or VUV radiation has its energy, and these electrons, while not being found in space as such, there's no electron radiation going on in space, can be very readily produced whenever energetic cosmic rays or energetic particulate radiation interacts with matter. So the secondary electrons that are produced if some X-ray or gamma ray or some very fast ion hits an ice grain, as in our case, will have energies in this range between, say, 5 and 20 electron volts. So, what can electrons do in chemistry? There are, in principle, 3 ways of inducing chemical change by means of electrons. The first one would be the creation of a cation by electron impact ionization. This is probably which many of you have done, something which many of you have done in the lab, because this is how most mass spectrometers will produce ions so they can be analyzed. Another process would be the neutral excitation. This can actually also be achieved by interaction with light, for instance. I'm not really going to talk about this part today, but what I'm also going to talk about is the attachment of an electron to form an anion. This is, of course, now something which you can't do with UV radiation, but since we can assume that there are at least some secondary electrons about, these electron attachment processes can be very interesting tools for chemistry. So mostly this is referred to as dissociative electron attachment, because these anions are in most cases very unstable, so they will dissociate. Well, just a one-slide description of what the experiment actually looks like. We have a UHV vacuum vessel that we can get down to about 10 to the minus 11 millibars, and we have a gold substrate in there, which we can cool down to about 35 K. On good days it can go to 30, but that's the general idea. We can then put one or several layers of one or several different gases on them, condense them, and irradiate them with an electron source that can, in theory, go up to 500 eV, but we've very rarely exceeded the 20 eV or so. And under this irradiation, products will form. So after irradiation, you're going to have a mixture of your starting materials, some product molecules, and then you take away the electron gun, you put in the quadrupole mass spectrometer, and then slowly heat up your sample to room temperature or even slightly higher, and you monitor with the mass spectrometer the stuff that comes off the gold. So we can actually take very, very small, very defined quantities of chemical species, let them react with each other in a rather confined phase space, and then study the products with mass spectrometer. So this is essentially like taking these Miller-Urey type experiments or these ice irradiation experiments that have been done a lot in the past years, taking them down to a very, very simple, very fundamental level where there's only very few molecules. So typically we're using maybe 10 or 20 monolayers of substance. So what we can achieve by that is not really a realistic prebiotic interstellar grain chemistry type of reaction, but what we can do is we can look at individual reactions and work out some mechanism and work out reaction kinetics. So hopefully, if we do that for a lot of different substances, we can come to some sort of understanding of how in these Miller-type or ice experiments reactions the formation of new species actually takes place. So, back to the synthesis of formamide. One of the data sets that you get out of one of those TDS thermal desorption experiments would be like this. So now here this is just the position of a gas, and then we heat the sample without any irradiation, and we can see that at a mass to charge ratio of 17, ammonia comes off once the sample is at about 100 Kelvin. Also at mass to charge 28, where the CO sits, there's at about 40, 45 Kelvin, the CO comes off. Now, if we do the same and we place an irradiation step in between, we can see that the amount of ammonia left in the film decreases, we can see that the amount of CO decreases, and we can see the formation of new products. In this case, something with a mass of 45 and with a mass of 29. And if you look at the NIST databank mass spectrum of formamide, you can see that the main peak is 45 and the next biggest is 29. Well, actually I think you can't see that properly, but there's a line here at 29. And the ratio of these signals fairly well matches the ratio of those. And together with the desorption temperature, which is at about 220 or so Kelvin, you can actually identify substances. Well, so if you do that for a lot of different electron energies, starting at 2, 4, 6 eV, you can see that there's some sort of energy dependence. Now, if we are looking for the mechanism, at first we can look at another database and find out that the ionization threshold for ammonia actually lies at pretty much 10 eV. So anything above this is probably due to electron impact ionization. But by doing some other experiments, we should assume that the yield would run something like this and then increase up to, say, 7 or 100 eV until it reaches a plateau. So all this stuff can't really be explained by electron impact ionization. So there is another mechanism, and we know that dissociative electron attachment to ammonia takes place at around 9 eV. These are pretty sharp resonances usually, and if you put those two together, you can actually explain how this energy dependence comes about. So there are two different ways of forming formamide, obviously. Well, the first one, the synthesis by electron impact ionization, is actually quite straightforward. So you have ammonia, you hit it with an electron, you knock out another electron, and you end up with a radical cation. This radical cation you can then attach to CO. So in principle, the reaction between ammonia and CO to give formamide is an exothermic reaction, so it should just run by itself. The problem is there's a very high reaction barrier because this multiple bond system is very electron rich, and the free electron, the lone pair of the ammonia is also very electron rich, and you just can't get them close enough to each other because of electrostatic repulsion. But if you turn one of them into a cation, it works like a charm. So you end up with a radical cation very closely resembling formamide already, and then by capture of another slow electron, one that is thermalized by hitting multiple molecules in the ice film, you end up with formamide. This is actually a pretty universal mechanism. You can use that to attach ammonia to a host of systems with double or triple bonds. This has been studied for acetylene, for instance, to give ethylamine, which is not terribly relevant to prebiotic chemistry, but it's technically a very important reaction. So the other mechanism by dissociative electron attachment attaches the electron to ammonia to give a radical anion. And that anion is unstable, and it will fall apart more or less 50-50 to give NH2 radicals and NH2 anions. Now, both of those, again, can, by a very similar mechanism, attach themselves to the multiple bond system of CO to give rise to some sort of transition state like this, which is then saturated by reattaching the hydrogen radical or anion and giving formamide. So there is, in conclusion, there are two ways of actually forming formamide from CO and ammonia in these kinds of reactions, and it is actually very easy to do. It is a lot easier to do in prebiotic chemistry to form this formamide than form an amino acid. So, as a rather provocative argument, one could say that maybe it is easier to form a peptide, which will later then give rise to amino acids by hydrolysis, than form all the individual amino acids and have them condensate, which requires a lot of aqueous chemistry and stuff. So the formation of peptide-like molecules should be, and I think we will do that, studied further by not taking just ammonia but small amines like methylamine, ethylamine, and see whether that reaction runs in much the same way, so you can end up with peptides that are a little more interesting than formamide, peptide-wise. Well, with that, it's time to end, and I'd like to thank you for your attention and for being here in such numerous quantities, and ready to take questions. Thanks.
Thank you.